Thank you very much. I'm not going to stand on the stage, otherwise I'll probably hit the ceiling. Right, I'm here to talk to you about testing and microservices, possibly. Or, as the real title of this talk is, Microservices and Pain. My name's David Dawson. I run a consultancy company called Simplicity Itself. We operate in many places. I live in Manchester, which is one of the reasons why I'm very happy to come and support this event. And kind of work with the Open Credo crew. I run the Microservices user group down in London, which is the biggest kind of a group of its kind in the world. There's several thousand members in there now. And so if you're ever down, I think the first Wednesday of the month, so we've got an event tomorrow. If you're ever down in London, come along, it'll be fun. Okay, so I'm going to start with a question. This is not rhetorical. What are microservices? You've heard some things already, reflect them back. Come on, throw some answers. No? No?
Small services.
Small, lines of code, bounded context, REST, all these things kind of play in, containers. So this is a good question because it's actually very hard to pin down what microservices are. So we actually did a review a while ago with all of our clients. What are microservices? I tried to figure out what they thought of when we said the word. And they came back with all of what I just said and a lot more. And going through all the results, we figured something out, which was none of them agreed with each other. And so this troubled us because we sell microservices as a business, so we need to understand what it is we're selling and what people actually think of. And then we saw a piece of commonality, two things that everybody agrees on. Everybody. The first one was isolation. So some kind of isolation using a network boundary, normally, unless you're into OSGI, at which point that goes out the window. But there's some kind of air gap, the idea that isolation will give us something, and that's what we're going to use. And then the other thing was aspiration. So the idea that the world will be better if we do this. So we're going to use isolation, and we're going to get a better world. And actually, that's it. That's all that anyone agrees on, which is a bit rubbish, to be honest. Kind of from a technical point of view, I'm a technologist. I want something concrete. I want something to play with. And this ain't it. This is not what I want. Or maybe it is, but we might have to take a different point of view. So I'll ask you a different question. Microservices architecture. People actually always say architecture, almost always. When you say microservices, they'll refer to the microservices architecture. And so this gives us something else to dig into. Microservices, isolation, aspiration, that's about it. Architecture, well, what is architecture? Is it the same thing as design? What do we think? This is a trick question. Sorry. So it's actually very easy to say, I think this is something that confuses people often, but I find it very easy to say that they are not the same thing. And it's very trivial to actually prove this using a cardinality check. We just count things. So design. You go and look at a code base, and you'll see all of the design decisions littered everywhere. And effectively, there's an unlimited number of them. If you go and design the same piece of software 6 months later, you'll make different design decisions. So as far as cardinality goes, unlimited. Architectures, well, there's recognizably only a few, maybe a few dozen that we kind of accept as architectures. And you start to think of things like end-tier, event architectures, all the other kind of weird and wonderful ones that you might come up with. But there's a limited number of them. And we agree generally that this is an architecture that we're going to implement. And so just from that cardinality check, they are different things. So that then leads to the question, what the heck is architecture? What is this thing that we're referring to? We've stolen a term from outside of software, and we've repurposed it for our own uses, but we've not defined it. Because architecture in terms of construction is well defined. In terms of software, less so. So when I think of architecture, I think of a set of mental tools that you apply to a problem. It's the route to your design. It's the way you engage with the problem. It's a set of constraints that the architecture group or whoever is doing that will have put on you as a software designer to actually deliver something. So it's the way that you approach the problem to create a solution. It's not the solution itself. Now, all of those things I've heard in another field. All of those things that I've just described, mental tools to approach the world and come up with a solution, they're all from philosophy. So you can say that this is a philosophical position that you're taking. And so I would actually say that architecture is, in terms of software, is philosophy. That's what you're buying into. And this is something substantial, because philosophy is not airy-fairy. You know, it's something that's been studied for many thousands of years, and we actually can do this very well now. And so in software, we can start to absorb all this philosophical information and start to do things with it. So if microservices is an architecture, then I would put it to you, microservices is a philosophy, and that gives us something to work with. We don't have to think of it in terms of, well, it's Docker plus some other stuff. We can actually think at a much higher level and start to use it as a lens that we can create a solution. So I'm going to give you an example of how philosophy, in terms of software, will actually change the way you design things, change your kind of decision-making process. And hopefully it'll kind of give you an insight as to why microservices is actually a good thing. It is solid. It is something that you can use. So, perfection. Now, you didn't know it until this talk, but you have a mind worm. You have a piece of knowledge that has been planted into Western thought in particular, that has been passed down over many, many generations, over millennia in fact. And it's this, the idea of perfection. And I'm going to tell you where it came from and what it's done to you. So, it was actually created by the Greeks, specifically by this man here, Plato. He came up with something that he called the theory of ideal forms. And it goes like this. What's this? It's a triangle. Yes, it is. Now, I could have drawn a different triangle where nothing actually matched that one, but you would recognize it as a triangle, which is interesting. This was something that he latched onto. We can have something that we say that's triangle, but every single concrete triangle that you look at is different. So what's this? It's a horse, it's a pony. And so this is actually the same thing. Every single horse, if you were to go and look at it, is different from every other horse. But you can look at it and say, horse. And so what Plato's kind of theory came to was, well, actually, there must be something else, which is this idealized form of horse. So that when I say to you, horse, right now you'll probably think of that. But if that picture wasn't there, then you'd think of something. Each one of you would be different, maybe, but you think of an abstract horse, an ideal form of horse. And according to the theory, that's the real horse. That's the real thing. That's the perfect horse. And that is the point at which perfection entered Western thought. It didn't actually exist before. And so we've been struggling with this concept of, well, perfection exists and we can get there. We've had that in our minds for millennia. We think perfection is real. You know, that it affects us in so many ways. But it's a lie. It's not something that's actually true. So in terms of where this leads, we have a story. What's this? It's Indiana Jones. What's behind them? Petra, yes. So the story of Petra is interesting. It's a city in the Middle East. It's currently abandoned. It was carved straight into the rock. This wasn't constructed, it was carved. And it's probably the largest example of what is known as monolithic architecture in the world. And so all of these buildings were just carved straight in. And specifically, they built a giant aqueduct system that shipped in water from 30 miles away into the city, also built monolithically. So it was built so that all the water would just flow in. They didn't construct them, they just carved them into the rock. And this was good, this worked. You know, it was a very successful city for a long time, until something happened, which was an earthquake around 400 AD, something like that. And the aqueducts cracked, and they couldn't be repaired. So this concept of, they thought they created the perfect city, but then change happened. You know, the world around them changed. Their aqueducts were destroyed, the city had to be abandoned within about 10 years, and it's never been reoccupied. And so we have this city, this great monument to perfection, and it's empty. And this is where really perfection as a concept has led us. You know, constantly thinking that we can see where we should go, and it's achievable. And it's completely bogus. I'm very sorry. And it's a mind worm that was planted in your thoughts millennia ago by the Greeks. So, perfection is a lie. You cannot see the future. You cannot predict it. That is simply the way it is. There is an alternate philosophical position that we could take. So, what's this? It's a river. In fact, it's the Tame River where I live, out to the east. So like I said, I am from Manchester, unlike certain southerners amongst us. And so the idea is, you look at this river, it looks pretty, it doesn't change very much. It's the Tame River, it was called that for a reason. But actually, if you look at this river now, everything is different from that picture. Absolutely everything. All the grass has been regrown, the trees will have moved, all the water's gone, all the ground underneath will have been shifted ever so slightly. It's a different river now. And so, a long time ago, a man called Heraclitus said this. He actually predated Plato by a while. And so, no man steps in the same river twice. And the idea is that change is constant. This is in fact the natural state of the world, change. So, if your reality is changed, then that's what you in fact should optimize for. Don't try and predict what's going to happen. In terms of what this actually looks like, as far as software goes, waterfall is perfection. That's what it's aiming for. The very idea that you could design it right, kind of get the requirements right, test it right, build it right, deliver it into production right, all in one long stream. That's the only reason people thought that could actually be done is because they believed in perfection as a concept. So really, I would say, your microservices as an architecture, as a philosophical position, go and read some Stoicism, get some Stoic philosophy into you, and you will have a much better software development life. So this was a lightning talk, right? No? Okay. Right. Okay. So we're going to switch from philosophy to some psychoanalysis. What pains you? For me right now, it's my throat. So, what hurts in microservices? Well, for the purposes of this talk, testing. Testing is something that's painful. We need to get it right. Testing microservices. Is this in fact a thing? Well, from my point of view, the reason I went through the whole philosophy arc there was to say that no, testing as far as microservices go isn't specific to microservices. You have to actually take a step back and what have you built? What have you designed? Test that. As far as microservices go, the really key one here is isolation. So when you go to kind of build microservices, then you will generally build a distributed system. And so that's what we need to kind of aim for. But before we do that, let's step into testing. Where did testing come from? Because we have to understand where we came from to understand what we're going to do. Who's ever been a manual tester? Yeah, it sucks. It's horrible. And this, in fact, was the only way that testing used to be done. And yeah, it's not a great world. Around 1989, this gentleman, Kent Beck, came up with the XUnit, first XUnit system. I think he built it in Smalltalk, but it might have been JUnit as the first one. And they came up with something as a kind of a testing style that we now refer to as classical or statist TDD. And so this essentially goes like this, where you have a class that we want to test, which is the one at the top. We invoke some action, it interacts with some kind of stub, with some kind of stubs behind the scenes, and then we ensure that the response that comes back from our code is correct. So we don't care about these other objects here. They're just there to stand in the way and provide data back. We don't test them, we test our code. This is classical TDD. So it's very much based on understanding how data is moving in and out of your code, not what anyone else is doing. So broadly, this is very good for algorithmic systems. If you want to test an algorithm and make sure that it works, this is the way you would do it. And in fact, this is the way that people really tried to do it for the first, 6 or 7 years of TDD. Around 2008-ish, 10-ish, depending on who you talk to, down in London, in financial companies, they were dealing with very stateful systems that were interacting with lots of other very stateful systems a lot. And so they came up with a different way of testing that we now know as Mockist, or the London School of TDD. And this looks very different. So we have some code under test, we invoke it, and then we ensure that the interaction with the runtime mocks down at the bottom is done correctly. So we're ensuring that our code interacts correctly rather than it sends something back to us. So it seems subtle, but it means that the way that you construct and design your code actually changes a lot. And your tests especially will change in their design a lot, depending on which brand of TDD you're doing. And it's worth mentioning these can be mixed. You know, kind of if you actually look through your code bases, you're probably doing a mixture of this. But it's also good to kind of take a step back and understand the history behind the two ways of doing things. So these are very much based on communication. So, now, microservices. One of the precepts of TDD is to say that if your code is hard to test, redesign it so that it's easier to test. You know, and that will have the effect of improving your design. Now, this is something that I think we've forgotten in microservices. You know, we're in this mad rush to develop services that look like kind of small SOA, or they use REST, or they use containers, or they use whatever brand of technology you're looking at. We rush into them, and then they become hard to test, and we begin to make excuses. Like some of the people I know, they will say, well, I don't really have to test my microservices that much because they're very small. Great. Now, as far as design goes, we've picked up a few different design styles of microservices that people are using. And so what I want to run through is just a couple of them. The first one, entity-oriented, which you probably know already. So this is what I'm banging on about, really, as far as design goes. Now, you're building a distributed system, so it'll probably look something like this. You'll have a whole bunch of different services, a whole bunch of different data stores. They'll all be interacting in various ways. And so we'll have things like bounded context popping up. And we need to test this stuff. How do you make sure that works? It's a good question. Glad you asked. So let's get rid of some of these things. Right, so what we need to do in this one, we have interaction lines here between our code and the services behind. So what we want to probably do is to do mock STDD. We want to make sure that our service is interacting correctly with the others. So I'm assuming HTTP here because that's currently still popular. To make this work, you would have to do all of these things. If you want to do a full stack test of your service interacting correctly with other services, then you will have to create some kind of mock system that your service is going to interact with. You'll have to start them up. You'll have to start your service. You'll have to interact with it, and then make sure that the mocks have been interacted with correctly. That's how you would do mock TDD with microservices, which is fine. Now, there's a few different ways you can implement this pattern. One of the big ones is using client libraries. So this is one of the big recommendations in microservices generally, is to actually, when you create your service, create libraries for it as well, and give those libraries out to your consumers. What this allows you to do is to replace that library and use it so that your service is talking to it, and you've replaced it with a runtime mock. So you don't actually have to start lots of processes up, you just change the library. Now that can work reasonably well. The problem is, you're not actually communicating with some remote systems, so certain kinds of failure scenarios you probably won't see, especially around networks. You know, kind of when you're using a distributed system, the network hates you, I'm very sorry. You know, it despises your existence. And so you'll get lots of failure scenarios appearing purely from that. A different way of doing kind of interaction testing like this is, instead of replacing the client library, you go in at the protocol level. So your service has to communicate with some other service using some network protocol. Often this is HTTP, but it could be something else. What you'll find is that you can dip in there and create some kind of replacement at the protocol level, which is what I'm talking about here, protocol replay. So there's some examples up there. One of the ones, I think, Betamax, the one in the middle, that's a very nice JVM-based system that allows you to replay HTTP conversations as part of a test. So the first time you run your test, it will actually really connect to the remote system. Betamax will then record it on a tape. The next time you kind of run that test, it will replay from the tape. So it means that your remote system does not need to be there, but your service thinks it is. It's a nice approach. Unfortunately, what it means is you have to kind of keep your system in sync with the remote, specifically around schemas. So schemas are one of the great pains of microservices. There's a few different approaches to making sure the remote and you agree on what the data should actually look like, but it's still a pain, and it's going to be a pain for a good long while. But we'll see. One of the things that actually, as I was preparing this talk, someone pointed out to me, this is not a mock. So I'm selling it as a mock, but it isn't. This is actually a stub. But hey. Finally, you could create full mock processes. So these are real systems, real services that stand up. Your application communicates with them, and then you can, in some way, draw some information out of the mock to assert that it's been interacted with correctly. So this will be the Mockito for the microservices age. And if you implement this, it works well. Implementing it is a pain. It's not easy, and there's kind of some issues with this as well. But if you can actually implement this kind of test, this is the most solid one, because you're testing the full system stack, which is good. So, if you want to actually do mock-is TDD in microservices with full mock processes, this is the kind of approach you would have to take, just like in any unit test. You start up your mocks, you run your interaction, you verify that the things have been interacted with correctly. Now, in terms of how you would actually do this, one of the best ways that we found of running this kind of test is to use Docker. So if you've ever come across Docker Compose, I haven't updated this for the V2 schema yet. But here what we're doing is orchestrating a test. So we have some kind of some kind of communication system, which is Rabbit. We have our service under test on a local Docker Compose environment, and then we have some kind of mock that we can set up and verify against, with these being those bits. So if you're doing any kind of orchestration, I strongly recommend you look at Docker Compose as part of your testing strategy. Last one on this is service virtualization. If you've ever kind of come across the idea of service virtualization, or if you never have, what this lets you do is create mocks. And you can then use them for a whole bunch of other things, but for testing, they can effectively stand in place of our runtime mocks. Now, I don't know about you, but I found that quite hard going. There was a lot there, and I kept on saying, this is a pain, this is a pain, this is a pain. Now, the design of the microservices that you saw is probably what you're doing now, where you have a service, it owns its own data, you interact with it using some kind of RPC, whether it's HTTP or not, it is still kind of an RPC style interaction. And so that's the root cause of all of this pain. You certainly can do this, and for any kind of RPC interaction that you're doing, this is what you would have to do. Now, I don't like this at all. I think that TDD is telling us possibly we need to reconsider our design, and then maybe testing can become easier. So another kind of service design that we've come across is what I like to call flow-oriented. You may have come across these as event-oriented or event-sourced or something like that, but the idea is the way the data moves is very different. And so that gives us a good way of hooking into our services in a different way to create an easier test. Excuse me. So who's ever built an event-based system? We have a smattering. Excellent. So have you ever gathered requirements from users? Probably. So when you're talking to users, they do not say, I want a message processor, and I want the message processor to asynchronously interact with the whatever. They don't say that. What they say is something more along the lines of, yeah, an order gets placed, and then after the order gets placed, the payment should be taken, and once the payment should be taken, then an email needs to be sent. That's what they say. And that, in effect, is events. It's things that should happen in the system, things that happen in the past in the system. So you're viewing it from the point of view of, these are the things that should have happened. This is the key to an event-based system. Kind of all the other things around asynchronous or messaging or anything else, none of them actually matter that much. It's the semantics of things that have happened in the past. Now, if you were to take this and actually view it in terms of a flow, then what you'll see is essentially a stream, like our river, things that happen. So in the case of our orders, you can see them flow past you. And then you can see the payments flow past you, and the notifications flow past you. And so you'll see lots and lots of things happening. And looking back, you can see lots and lots of things have happened. All these events there lining up for us. So looking at our order stream, we were kind of looking at the design of systems before. We called them entity-oriented. They own the data. You could look inside them and say, actually, this order is there. Now, that still exists in this kind of view of the world. It's just it's spread out, a series of operations, just like Dominic was talking about before. And so these operations, they're our entity. It's still there. We just have to present it in a different way. So the way we can actually take this data and present it to the world, well, we take that set of operations, we play them into some kind of service, it just goes chunk, 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 chunk. Say, create a new entity here, there is our entity, it's here. But the point of persistence, the point of durability, the actual golden source of truth in the system is no longer in our service, it's in our event stream. Now, the reason I'm saying this is this gives you some options in terms of design. And those changes in design will give you some options in terms of your testing as well, which we'll get to in a second. But once you have an event stream being played into one service, well, you can play it into an arbitrary number of services. They will all be kept, just as Don was saying before, they'll all be kept in sync. They'll be eventually consistent with each other. That does not mean inconsistent. It's a very different thing. Eventually consistent is consistent at a certain point in time. So whenever you ask a question of an eventually consistent system, you should always include a time parameter and say, what is the state as of X? And you will always get the same answer. So looking at this, something interesting struck us when we were building event source systems a few years ago, which is we have our different streams and we have things that happen. Naturally, what you'll start to see is just as we had our list of events before, they'll start to link up. You'll start to create causal relationships, not just time-based ones, which is the stream, but actually this happened, and then this happened because of this. And so these causal relationships give us an interesting option in terms of testing. So we have our event chain. And if you attach the appropriate information to the event, you can start to see where it came from. Where were these events actually spawned from originally? What reacted to an event to create another one? So we can actually see our system dependencies purely from the data. We don't actually need to know the interactions anymore at runtime. We can just look at our data and start to see that, yes, these interact in nice ways. As far as testing goes, this gives us a huge thing. Because what we can do, originally we would have had to actually create all of these services up, stand them up, run a test, make sure that they all interacted with each other in the correct way. We don't need to do that anymore. So you have to remember what we're actually looking at is a series of streams that are being operated on by a set of services. So we've got two things to think about, the streams of data and then our actual runtime processes. And so what we can do is effectively pull in the bounds of our test. Now the reason for this is that our service in the middle, the payment processor, it's reacting to an event and it's spawning an event off as its output. So if we can stand up our single service, fire an event, which is our order placed, we expect it to do something, and then fire another event off, which is our payment taken. That's all we have to do, event in, event out. How it interacts with anything else in the world, I don't care. As far as my test goes, this is it. Now, as far as an event-based system test, which is what I've just described, this is the way you would do it. So you create your initial event kind of setup in your data store, whichever it is. You would then run your service up, wait for the event to come out, and then verify that that event that's come out is correct. So you're purely operating on the data. Now, what this has done is actually created effectively an integration test between your service that you're testing and the other services that it's interacting with via events. I think you could possibly argue that, but we're hooking into the interactions and we're replacing them with events rather than RPC. And it's a far, far easier thing to test. To make this work, you need an event store. You need some kind of event chain, kind of database. Now, Neo4j is excellent for this. Any kind of graph database, you can model this kind of data very, very easily. And then you need some kind of testing system, which you'll be constructing your own, I'm sure. So what I've shown you there is two different ways of testing microservices systems. Classical and mockist. We started off with a mockist approach, and that was driven by our system design. So our design was very much entity-oriented. We had lots and lots of interactions between the various systems, probably using HTTP or something similar. Changing your design means that you can also change your testing approach. So you can go back to a kind of a classical statist way of testing, where you put some data in, you get some data out. Nothing else matters. How things interact, well, that's just an implementation detail. It's not the actual point of the test. Yep. Okay, so there we go. That's the end of my talk. If you have any questions, we have 10 minutes.
Anytime, David, yeah. Got a good 5 minutes for questions. If you wouldn't mind repeating any questions, David. Well,
of course.
For the mic, thanks for the video, sorry. Questions at all?
Man at the back.
Right. Modeling events and chains in a graph, basically.
Yes.
How do you extract, or how do you detect the chains character of events across different streams? So how do you build up that, what's it that connects things, or enables you to connect things?
So the question is, how do you actually create the chain? And how, from a data point of view, how do you construct it and store it and all that kind of area? That's an excellent question. So generally what we're doing when we build an event-based system, you have to define what an event is. So an event, in terms of how you design it, tends to be, if you look in all the literature, what they'll tell you to do is create some kind of type, or some kind of type, which would be payment taken. That should always be in the past. It should have a timestamp attached to it, and probably some kind of unique identifier. And then a payload, which is kind of what the actual data of the event is. We would tend to extend that with two pieces of information, which is a caused by, which is a reference to another event that caused it, and then the service that generated that event. Once you have those two extra bits of information in all of your events, you can do what I've just described, and then a whole bunch of other analysis as well. Kind of understanding what services are struggling, what services are piling up, are being slow in responding, all kinds of information like that you can extract purely from data. You don't actually need to see the services themselves to kind of gather that information. Does that answer your question?
Yes.
Yes.
Unless you pass your event through each of your chains, how do you know that the event or the process before is producing the right thing for the next? All you're actually doing is passing a manufactured event into a piece of software.
Yep.
You're testing that particular thing, but you're not testing the chain as a whole.
Yes, precisely. So it's essentially the question, or the assertion is that by running a test, as I showed you, constrained, if you put an event in and wait for an event to come out, you're not testing the entire business process as a whole. And you're completely correct, absolutely. So that's why I kind of backtrack slightly on it's an integration test, kind of, because you are correct in that. If you want to ensure that the entire chain works, you do have to check all of the interactions. However, I would say you can construct the tests very differently. You don't have to fire up all of the services at once. You can put one event in, fire a service up, whatever its output, using the next test. And then you can kind of test it in an async way. But yeah, you are correct. Any more questions? Is that good? Brilliant.
No. Thank you very much.
Thank you very much.